Hello friends, today we'll be talking about Sturm's conoid. Now let us first understand what is Sturm's conoid and what is its utility. So, whenever there is a plane surface, the parallel rays of light goes through it and the rays of light are focused at one point. So consider a perfect optical condition where the patient is a emmetrope. The parallel rays of light are going without any accommodation, without any bending, and they are now focusing at one point on retina. Okay. So what happens when parallel rays of light are refracting through a toric, through a astigmatic surface? This is all about Sturm's conoid. So a toric or a astigmatic surface is when you have a vertical meridian, and when you have a horizontal meridian, isn't it? So it has curvatures at two different meridians. This is your astigmatic or your toric surface. Now what happens when the rays of light goes through it? This is your Sturm's conoid. So consider that there is cornea, we have a vertical curvature, we have a vertical meridian, we have a horizontal meridian. We know the refractive power are not same. Now obviously the vertical meridian is more curved. That is why when the parallel rays of light are entering, are passing through, they are being focused earlier, isn't it? So this is your focus number 1. Okay. So before that, what happens at point number A? So just closely look at point number A. If we see at point A, the vertical rays and the horizontal rays both are converging, isn't it? But the convergence of vertical rays is much more as compared to the convergence of horizontal rays. The C here is not curvature, it is convergence. Okay. So the convergence of vertical rays is much more as compared to the convergence of the horizontal rays. That is why the resulting image will be a horizontal oval. Okay. This is what is happening to that light rays at point A after refraction. Now what happens at point B? So see that at point B, the vertical rays which are being converged, they have come to a point of focus. So this will be your focus number 1. Now when vertical rays have come to a focus, it is only the horizontal rays which are now not converging. So the resulting image will be a horizontal line because the horizontal rays are still converging. So this is your point number B, which is a horizontal line. Now what happens at point number C? Let us see closely. So at point number C, if you see closely in this picture, at point number C, the vertical rays have start diverging, isn't it? Vertical rays after coming to a focus have start diverging. So this is your vertical diverging, but your horizontal rays are still convergent. Now here, the amount of vertical divergence is exactly equal to the amount of horizontal convergence, isn't it? Can you see this? So the amount of convergence of the horizontal rays is actually equal to the amount of divergence of the vertical rays. This creates an image which is a circle, and this circle is known as circle of least diffusion. This is a very important question. Circle of least diffusion lies at which point? So here in this figure, it lies at C point. So friends, you may be given another figure where it may be at some other point, but you have to see closely where is the point, where is the circle of least diffusion, and the circle of least diffusion would be where the vertical divergence is absolutely equal to the horizontal convergence. Okay. Now let's see what is happening at point number D. At point number D, the vertical divergence is much more as compared to the horizontal convergence. So the resulting image is a vertical oval. Okay. Now what is happening at point number E? At point number E, the vertical rays are diverging. Can you see? Vertical rays are diverging. And this horizontal rays have come to a focus. Horizontal rays have come to a focus. So this will be your focus number 2. That was your focus number 1. This is your focus number 2. Now, here the resulting image will be a vertical line because the vertical rays are still working, they are still diverging. Okay, so this is your Sturm's conoid. This is your circle of least diffusion, and the distance between the focus number 1 and the focus number 2 will be called as the focal interval of Sturm. Okay, so this will be called as the focal interval of Sturm. Now friends, why do we read that? What is the importance of Sturm's conoid? Why are we reading? Okay, so basically the clinical application of Sturm's conoid is that considering when one patient is having an astigmatic refractive error. Now in astigmatic refractive error, obviously we have to give cylindrical glasses, or the patient has to be given a toric glasses. Now whenever we give glass to the patient, we want that he should have a good fine image. So this fine image, for this fine image, we want that circle of least diffusion should be formed at the retina. We place the glass at such a level that the circle of least diffusion should be at retina. So this is the point where the patient gets the best image. Okay, the patient gets the best image. So this is the clinical implication of Sturm's conoid, that the circle of least diffusion should fall on the retina. Okay, so that's it.